Our universe is not what it seems. For most of the last century, we thought we had it figured out. A grand cosmic clockwork of stars and galaxies, all moving under the familiar pull of gravity. But then came a discovery so profound it shattered that serene picture. Scientists realized most of the cosmos is made of stuff we cannot see. A missing ingredient so vast it forced us to rewrite the rules of reality itself. This is the story of the invisible mass problem, a fundamental crisis that transformed modern cosmology. By the end, you will understand how the hunt for this hidden universe led us to the revolutionary and deeply strange concepts of dark matter and dark energy. We will trace the journey from the first confusing clues in spinning galaxies to our current model of a cosmos dominated by mysterious, unseen forces. What do you think it means to live in a universe where almost everything is hidden from view? It was a time of extraordinary confidence for cosmology. By the 1950s and 60s, the scientific community felt it was finally piecing together the universe's grand design. The primary actor in this cosmic drama was gravity, the same force that holds you to your chair and keeps the moon circling Earth. And the only players that mattered, it seemed, were the ones you could see: the brilliant stars, the swirling galaxies, the glowing clouds of gas. All of it was thought to be made of ordinary matter, the same protons, neutrons, and electrons that make up you, me, and everything around us. This was the luminous mass model, a beautifully simple idea. The universe was a vast collection of luminous islands, all moving under the mutual gravitational pull of their combined visible light. Astronomers could measure the light from a galaxy, estimate how many stars that light represented, and from that calculate the galaxy's mass. That mass, in turn, dictated how fast stars should orbit the galaxy's center, just as the sun's mass dictates Earth's orbital speed. It was a closed, elegant system. The mathematics were clean, the predictions were clear, and for a while the observations seemed to agree. This consensus created a powerful illusion of stability. The cosmos appeared to be a knowable, predictable place, a clockwork universe whose every tick and tock was governed by the gravity of what shone in the darkness. It was a comforting picture, a culmination of centuries of astronomical thought. But like many comforting pictures, it was incomplete, and the cracks in this serene facade were about to appear in the most unexpected of places, within the stately rotation of a humble spiral galaxy. The first serious challenge to this luminous universe came not from a single galaxy, but from a bustling crowd of them. In the 1930s, a brilliant and often combative astronomer named Fritz Zwicky turned his telescope toward the Coma Cluster, a dense swarm of thousands of galaxies millions of light years away. Zwicky had a clever way to weigh this entire cluster. He applied a principle from physics called the virial theorem, which, in simple terms, states that in a stable, gravitationally bound system, you can estimate its total mass by observing how fast the individual members are moving. The faster the galaxies within the Coma Cluster zipped around, the more mass you would need to hold the entire cluster together against their own motion. It was like watching children running around a playground. The speed of their play tells you something about the strength of the social glue, the unseen rules that keeps the group from flying apart. When Zwicky did the calculations, the result was staggering. The mass required to keep the Coma Cluster gravitationally bound was absolutely enormous, hundreds of times greater than all the mass he could possibly account for by adding up the light from every single star in every single galaxy. There simply was not enough visible stuff to provide the necessary gravitational glue. He called this discrepancy dunkel materie, or dark matter. But here is where the story takes a curious turn. The scientific community of the time largely dismissed Zwicky's finding. They saw it as an oddity, a puzzling outlier that was probably the result of an error in his method or a misunderstanding of the complex dynamics at play in such a distant cluster. The idea that the vast majority of matter in the universe was completely invisible, that everything we could see was just a tiny fraction of reality, seemed too radical, too unsettling for the established luminous model to accept. So the clue was filed away, a curious footnote for a future generation to reconsider. The universe's deepest secret had whispered its name, but for decades almost no one was listening. The luminous universe model was so compelling it took another 40 years for the problem to truly hit home. This time, the challenge came not from distant, chaotic clusters, but from the serene beauty of our own galactic backyard. In the 1970s, astronomer Vera Rubin and her colleague Kent Ford turned their attention to individual spiral galaxies like our own Milky Way. They were interested in a fundamental question of cosmic motion. How fast do stars orbit the center of their galaxy, and how does that speed change as you move outward? The prediction from the luminous model was beautifully clear and intuitive. Picture our solar system. The planets closer to the Sun, like Mercury and Venus, orbit at blistering speeds. Those farther out, like Neptune and Pluto, move in a much more stately, slow fashion. This pattern, described by Johannes Kepler centuries earlier, arises because the Sun's gravity weakens with distance. Almost all of the Sun's mass is concentrated at its center. Astronomers fully expected galaxies to behave the same way. The bright, central bulge of a spiral galaxy contains most of its visible stars and therefore most of its observable mass. So, stars orbiting near that center should whip around quickly, held by a strong gravitational pull. But stars out in the faint, sparse spiral arms, far from the central mass, should orbit much more slowly, just like distant planets. This was the expected Keplerian fall-off, a graceful decline in orbital speed with distance. What Rubin and Ford measured, however, defied all expectation. Using a sophisticated spectrograph, they carefully charted the rotation speeds of stars from the inner regions all the way out to the dim, outermost edges of spiral galaxies. The data revealed something astonishing. The rotation curve was flat. Whether a star was close to the bright center or far out in the galactic suburbs, it was orbiting at roughly the same high speed. This was as if Mercury, Earth, Jupiter, and Pluto all raced around the Sun at nearly identical velocities. It made no sense under the rules of visible gravity. The only possible explanation was that there was far more mass in the galaxy than the light revealed. To keep those outer stars whipping around so fast, a tremendous amount of unseen gravitational force had to be holding them in. This implied that spiral galaxies were not just disks of stars, but were embedded within enormous, invisible spheres or halos of some mysterious material. This material exerted its gravitational pull far beyond the last visible star, shaping the entire galaxy's rotation. Rubin's meticulous work brought the invisible mass problem out of the realm of distant curiosities and into the heart of every spiral galaxy we could see. The evidence was now undeniable and universal. Yet the evidence for this hidden mass was still indirect, inferred from the motion of stars. To truly confirm its existence, scientists needed a way to weigh the cosmos directly, to feel its gravitational pull with their own instruments. They found this cosmic scale in one of the most elegant predictions of Einstein's theory of relativity, a phenomenon called gravitational lensing. Einstein proposed that massive objects do not just pull on matter, they warp the very fabric of space and time around them. Think of placing a heavy bowling ball in the center of a taut trampoline. The trampoline fabric stretches and curves. Now, roll a marble across that curved surface. Its path will bend not because of a direct force, but because it is following the contours of the distorted fabric. Light, Einstein realized, behaves like that marble. When light from a distant star or galaxy travels through the universe, its path is not perfectly straight. If it passes near a massive object like a galaxy cluster, the warped space around that cluster acts like a lens, bending and distorting the light's trajectory. This is gravitational lensing. For decades, it remained a beautiful theoretical idea, but with powerful telescopes like the Hubble Space Telescope, astronomers began to see it everywhere. They would point at a massive foreground galaxy cluster, and instead of seeing a clean background, they would see strange, stretched, and smeared arcs of light. These were not flaws in the image. They were the distorted, magnified, and often multiplied images of galaxies that lived far behind the cluster, their light bent around the cluster's immense gravity like a funhouse mirror. This distortion became a precise tool for measurement. By carefully analyzing how severely the background light was bent, astronomers could calculate exactly how much mass was in the foreground cluster causing the distortion. It was a direct measurement, a cosmic scale that weighed the cluster by the sheer amount of space it warped, and the results were unequivocal. Every time, the mass measured by gravitational lensing was vastly greater, often by a factor of 5 or 10, than the mass you could account for by adding up every single visible star and every wisp of glowing gas in that cluster. Here was a third, completely independent line of evidence, one that had nothing to do with the motion of stars or galaxies. It measured gravity's fingerprint directly on the fabric of reality. The verdict was in, and it was unanimous. The universe was filled with something massive, something that warped space, something that held galaxies and clusters together, yet emitted no light of its own. This was not an error, not an anomaly, and not a misunderstanding of gravity on small scales. It was a fundamental feature of the cosmos. The hunt was now official. We had proven something was there. The next far more difficult question was, what in the world could it possibly be? The evidence had become an avalanche, impossible to ignore. From the frantic dance of galaxies within distant clusters to the stubbornly flat rotation of every spiral galaxy, and finally confirmed by the warped light of gravitational lensing, the message was the same. Our cosmic ledger was catastrophically unbalanced. For every ounce of matter we could see, shining in the vast darkness, there seemed to be 5 or 10 ounces of something else, something that left no trace in our telescopes but whose gravitational signature was everywhere. This was no longer a curious puzzle. It was a full-blown crisis in cosmic accounting. Astronomers were forced to conduct a complete inventory of the universe, and the numbers they came up with were humbling, even shocking. When you add up every single star in every single galaxy, every glowing cloud of interstellar gas, every planet, and every speck of dust that reflects or emits any form of light or radiation we can detect, it amounts to less than 5% of what the universe actually contains. Think of it this way. If the total mass and energy of the cosmos were represented by a $100 bill, everything we have ever seen with every instrument ever built, every beautiful nebula and brilliant quasar, would be worth less than $5. The remaining $95 is entirely invisible to us, and this discrepancy is not a quirk of a few strange objects. It is a universal feature, a fundamental rule that applies from the smallest, faintest dwarf galaxies orbiting our own Milky Way to the largest, most massive superclusters of galaxies stretching across billions of light-years. Wherever gravity shapes the cosmos on a grand scale, this hidden mass is there, pulling the strings. The question had shifted dramatically. It was no longer about proving something was missing. The universe had presented its bill, and we were 95% short. The real mystery, the profound challenge that would define modern cosmology, was figuring out what could possibly make up that staggering, invisible difference. Faced with such overwhelming evidence, scientists had no choice but to propose a radical answer. They named it dark matter. This was not just a placeholder for our ignorance, but a specific, testable hypothesis. Dark matter was envisioned as a new, fundamental form of matter that permeates the entire cosmos. Its defining property is profound simplicity. It interacts with the universe through gravity and gravity alone. It does not emit, absorb, or reflect light. It does not bump into atoms or create friction. It is utterly invisible to the entire electromagnetic spectrum, which is why our telescopes from radio waves to gamma rays had missed it completely. Think of it like a vast crowd of silent, ghostly spectators filling a cosmic stadium. You cannot see them, you cannot hear them, and if you walked through them, you would feel nothing. But their collective mass warps the space of the stadium itself, altering the paths of any visible objects moving through it. That gravitational footprint was the only way we knew they were there at all. Of course, the first instinct was to look for simpler, darker versions of the ordinary matter we knew. Could this missing mass be made of massive, compact objects lurking in the darkness? Astronomers dubbed these candidates macho for emissive compact halo objects. This category included things like black holes, neutron stars, rogue planets that had been flung from their solar systems, and faint, failed stars called brown dwarfs. These objects would be dark but would still be made of the familiar protons and neutrons of ordinary matter. For over a decade, teams used a technique called gravitational microlensing to hunt for them, watching for the brief telltale brightening of a background star as a macho passed in front of it and magnified its light. The results were definitive. While a few such objects were found, their total mass was a tiny, insignificant fraction of the missing gravity. Macho could not solve the problem. The universe's hidden bulk was not made of dark clumps of ordinary stuff. It had to be something far more exotic, something that was not just dark, but fundamentally different from anything we had ever touched or seen. The door to an entirely new realm of physics had been pushed open. If dark matter is not made of familiar particles, then what is it made of? The most compelling answer points to an entirely new class of elementary particle, one that has never been detected in any laboratory on Earth. This idea transforms the hunt from astronomy into the realm of fundamental physics. The leading theoretical candidate for this ghostly substance is known as a WIMP, an acronym for Weakly Interacting Massive Particle. The name itself describes its proposed properties perfectly. First, it would be massive, meaning it carries significant weight, providing the gravitational heft needed to shape galaxies. Second, and most importantly, it would be weakly interacting. This means it ignores almost all the forces that govern our everyday world. It would not feel the electromagnetic force, so light would pass right through it. It would not feel the strong nuclear force that binds atomic nuclei together. Its only possible interaction, aside from gravity, would be through the weak nuclear force, the same subtle force responsible for certain types of radioactive decay. This incredible aloofness is exactly why WIMP could fill the universe yet remain so perfectly hidden. They would stream through our planet, our homes, and our bodies by the trillions every second without a trace. The beauty of the WIMP hypothesis is how neatly it fits into the cosmic story. Theories suggest that in the searing heat of the Big Bang, these particles would have been forged in enormous numbers. As the universe cooled and expanded, their weak interactions would have caused them to naturally fall out of thermal equilibrium, leaving behind precisely the amount of dark matter we observe today. It is an elegant solution that solves two puzzles at once, the nature of dark matter and a question in particle physics. Of course, WIMP are not the only idea on the table. Other theoretical particles are also in the running. There are axions, hypothetical ultra-light particles conceived to solve a different puzzle in quantum physics. There are sterile neutrinos, heavier, more secretive cousins of the nearly massless neutrinos we know. Each candidate has its own unique signature and would shape the cosmos in subtly different ways. The search has become a grand experiment, testing the very edges of our understanding. We are no longer just looking for a missing ingredient. We are probing for the fingerprints of a shadow universe made of particles that have been hiding in plain sight since the dawn of time. But what is the purpose of this vast, invisible presence? Why does the universe need so much dark matter? The answer lies in the very architecture of the cosmos we see today. Dark matter is not merely a passive ingredient. It is the master builder, the essential scaffold upon which every star, galaxy, and cluster was constructed. To understand its role, we must journey back to the universe's infancy, a time of near-perfect smoothness. In the first moments after the Big Bang, matter and energy were distributed with astonishing uniformity, like a fine, almost featureless mist. Yet today, we live in a universe of breathtaking complexity, with galaxies gathered into clusters, clusters linked into vast filaments, and enormous voids of empty space in between. This magnificent cosmic web did not form by chance. It required a gravitational blueprint, a framework to guide the ordinary, luminous matter into place. That framework was provided by dark matter. Because dark matter does not interact with light or radiation, it was immune to the intense pressure that filled the early universe. While ordinary matter, a hot plasma of protons and electrons, was buffeted by blinding light, dark matter remained serene and still, feeling only the gentle tug of gravity. This gave it a critical head start. Tiny quantum ripples from the Big Bang, minute variations in density, were amplified solely in the dark matter. These specks of slightly higher density began to attract more dark matter through gravity, growing slowly and steadily over hundreds of millions of years. They formed vast, invisible wells of gravitational potential, a cosmic skeleton long before the first star ever ignited. This invisible scaffold is what we call the cosmic web. Only later, as the universe expanded and cooled, could ordinary matter, now able to clump together without being torn apart by radiation, fall into these pre-existing dark matter wells. The dark matter halos acted as gravitational traps, collecting the gas that would eventually condense, fragment, and ignite into the brilliant galaxies we observe. Without dark matter's early, patient work, the force of gravity acting on visible matter alone would have been far too weak to form any significant structures within the lifetime of the universe. Galaxies might never have coalesced, or they would be rare, tiny, and scattered. The majestic spirals and colossal clusters that fill our telescopes are therefore not just surrounded by dark matter, they are its children, born within the invisible cradles it built. The luminous universe is a later addition, a glittering decoration hung upon a framework we cannot see, but whose shape defines everything. But if dark matter is truly everywhere, flowing through us in an endless cosmic river, then why can't we just reach out and catch it? This is the audacious goal of a global scientific endeavor known as direct detection. Imagine trying to hear a single, faint whisper in the middle of a roaring hurricane. That is the scale of the challenge physicists face. Their strategy is one of profound patience and exquisite sensitivity. They have built the quietest rooms in the universe, not by silencing sound, but by shielding their experiments from the constant, chaotic noise of ordinary reality. These detectors are technological marvels, often housed a mile or more beneath the Earth's surface, in abandoned mines or deep underground laboratories. The thick rock overhead acts as a natural filter, absorbing the relentless hail of cosmic rays from space that would otherwise drown out any subtle signal. Inside these silent caverns, the heart of the experiment awaits. One of the most promising designs uses large vats of ultra-pure liquid xenon, a noble gas kept at freezing temperatures. The principle is straightforward in theory, but staggeringly difficult in practice. The scientists are waiting for a dark matter particle, perhaps a WIMP, to drift through the tank and by sheer chance bump into the nucleus of a xenon atom. This collision, this tiny transfer of energy, would be the smoking gun. It would cause a minute flash of light and a release of electrons, signals that ultra-sensitive photodetectors lining the tank could, in theory, pick up. Experiments with names like LUX, Xenon, and Panda X represent the cutting edge of this quiet hunt. They are monuments to human ingenuity, each generation larger and more sensitive than the last. The Xenon experiment, for instance, uses several tons of liquid xenon, a vast target to increase the odds of that one in a trillion interaction. Yet, despite years of operation and phenomenal sensitivity, these detectors have heard only silence. They have not yet registered a definitive dark matter event. This profound non-detection is itself a crucial piece of data. It tells us that if dark matter particles are WIMP, they interact even more weakly than our best theories predicted. Each empty run narrows the field, pushing the possible properties of these ghostly particles into ever more elusive territory. The hunt continues in deeper silence with larger tanks, purer materials, and even more desperate hopes, because the reward for hearing that one cosmic whisper would be nothing less than a direct handshake with the hidden universe. While one group of scientists listens in profound silence underground, another looks to the sky, hoping to see the fireworks. This is the strategy of indirect detection, a search not for the dark matter particle itself, but for the aftermath of its destruction. The theory offers a tantalizing possibility. If dark matter is its own antiparticle, then when two particles meet, they could annihilate each other in a flash of energy, transforming their mass into a cascade of secondary particles we can detect. Alternatively, a dark matter particle might be unstable and slowly decay over cosmic timescales, producing a faint but steady stream of radiation. In either case, the ghost would leave a signature in the light. To find it, astronomers turn their telescopes toward places where dark matter should be most densely packed, where the chances of these rare interactions are highest. The heart of our own Milky Way is a prime target, a region where theorists believe a vast concentration of dark matter swirls around the supermassive black hole. Dwarf galaxies orbiting the Milky Way are even better laboratories. These faint, ancient galaxies are dominated by dark matter, with very few stars to create confusing astrophysical background noise. They are considered pristine dark matter reservoirs. The hunt involves scanning these regions with every type of eye we have. Gamma-ray telescopes, like the Fermi Space Telescope, search for bursts of the highest energy photons, which could be the direct product of annihilation. Radio astronomers look for synchrotron radiation, the glow emitted by electrons spiraling in magnetic fields, electrons that might have been created by dark matter interactions. Even experiments that detect neutrinos, those nearly massless cosmic ghosts or cosmic rays, high-energy particles from space, are on alert. They are searching for an unexplained excess of these particles coming from dark matter-rich regions, a signal that cannot be explained by any known astrophysical process like pulsars or supernova remnants. It is a meticulous process of cosmic forensics, looking for a specific pattern of evidence at the scene of a hypothetical crime. So far, a few intriguing anomalies have sparked excitement, like an unexplained excess of gamma rays from the galactic center, but none have risen to the level of definitive proof. The challenge is immense, separating a potential dark matter signal from the riotous background of ordinary cosmic phenomena. Yet this skyward search provides a crucial cross-check. If a signal is ever seen in the sky that matches what is sought underground, the case for dark matter would shift from compelling to confirmed. But what if the answer lies not in the silent cosmos or deep underground, but in a machine of our own making? This is the promise of the world's most powerful scientific instrument, the Large Hadron Collider. Nestled in a circular tunnel beneath the border of France and Switzerland, this 17-mile ring is not a telescope. It is a time machine, a portal to conditions that have not existed since the first fractions of a second after the Big Bang. Here, physicists are attempting the ultimate alchemy to create dark matter from pure energy. Their strategy is one of controlled, magnificent violence. They take protons, the hearts of hydrogen atoms, and accelerate them in opposite directions to within a whisper of the speed of light. Then, at 4 specific points around the colossal ring, they steer these beams into a head-on collision. When 2 protons moving with such unimaginable energy smash together, they do not simply break apart. They dissolve into a fireball of pure energy, a microscopic recreation of the universe's searing birth. And from that energy, new particles can condense into existence, particles that may have roamed freely in that primordial fire, but have long since vanished from our cold, expanded cosmos. The hope is that among those newly forged particles could be the elusive constituents of dark matter. The challenge, of course, is that if dark matter is truly invisible and non-interacting, the detectors surrounding the collision points will not see it directly. It would simply fly away, carrying its energy and momentum with it into the darkness. So, scientists must hunt for it by its absence. They meticulously account for every shred of energy and every direction of movement for all the particles produced in a collision. It is a perfect cosmic accounting ledger. If the books do not balance, if there is a significant amount of energy and momentum that simply vanishes from the detector without a trace, that missing signature could be the ghostly fingerprint of dark matter particles escaping. It would be like hearing the sound of a collision in a dark room, seeing debris fly out in all directions, but noticing that one piece of the wreckage is mysteriously, silently absent, having passed through the walls without a sound. The Large Hadron Collider has already reshaped physics, famously discovering the Higgs boson in 2012. Its ongoing quest is to push into even more uncharted territory, to energies and intensities where the rules may change and new particles may reveal themselves. Every collision is a roll of the cosmic dice, a chance that for a fleeting moment we might not just detect the hidden universe, but briefly bring it to life in a laboratory on Earth. Yet for all the ingenious searches, the silence remains profound. This very silence has given rise to a radically different school of thought, one that dares to ask a question that challenges a foundation of physics itself. What if there is no missing mass at all? What if instead our understanding of gravity is simply wrong? This is the provocative premise of modified Newtonian dynamics, or MOND. Proposed in the 1980s by physicist Mordechai Milgrom, MOND suggests we are not hunting for ghosts, but reading the equations incorrectly. For centuries, from Newton to Einstein, our laws of gravity have been spectacularly successful, predicting the orbits of planets and the bending of starlight. But Milgrom noted something crucial: every single test of these laws had been conducted in regions of intense gravity, near stars and planets, or in the relatively strong pull within our solar system. What if gravity behaves differently in the extreme weak fields found in the outer reaches of galaxies, where the acceleration from gravity is billions of times fainter than what we feel on Earth? MOND proposes a simple but profound modification. It introduces a new, very tiny threshold of acceleration. Above this threshold, in strong fields, Newton and Einstein reign supreme. But below it, in the realm of the incredibly faint, the force of gravity changes, becoming slightly stronger than the standard laws predict. This single tweak to the math has a startling consequence. When you apply MOND-modified equations to a spiral galaxy, you no longer need any invisible matter to explain its flat rotation curve. The extra gravitational kick provided by the modified law is exactly what is required to keep those outer stars whipping around at high speed. It is as if we had been using a map that was perfectly accurate for navigating a city, but failed miserably for crossing an ocean, not because the ocean was filled with invisible land, but because our map omitted the rules of currents and tides. For its supporters, MOND's initial success was elegant and compelling. It solved the rotation curve problem with a single adjustment, without invoking an entire universe of unseen particles. It made a clear prediction: galaxies with lower overall mass and therefore weaker gravitational fields should show the effects of modified gravity more clearly. Intriguingly, many of these faint, low surface brightness galaxies do indeed have rotation curves that align beautifully with MOND predictions, often with no need for fine-tuning. For a time, it presented a genuine, simpler alternative to the dark matter paradigm, suggesting that the mystery was not in the cosmos, but in the pages of our own physics textbooks. The elegance of MOND, however, faced a battery of tests far beyond spinning galaxies. For any theory to truly explain the cosmos, it must account for all the evidence, not just the puzzle that inspired it. And as cosmologists turned their attention to the largest scales and the earliest moments, MOND began to encounter profound difficulties. The first major challenge came from a violent cosmic accident observed in the early 2000s, the Bullet Cluster. This is not a single object, but the aftermath of a high-speed collision between two enormous galaxy clusters. The event was so energetic it ripped the ordinary matter apart. The hot, X-ray emitting gas from each cluster, which contains most of its visible mass, slammed together and stalled in the center, like two clouds of smoke colliding. But the galaxies themselves, along with something else, passed right through. Astronomers mapped the cluster's total mass using gravitational lensing, creating a map of where the gravity actually was. The result was startling. The peaks of gravitational mass were not centered on the glowing clouds of gas where the visible matter was concentrated. Instead, they were aligned with the locations of the galaxies which had sailed ahead. This meant the majority of the mass, the source of the gravity bending the light, was physically separated from the majority of the visible stuff. For dark matter, this made perfect sense. The weakly interacting dark matter particles from each cluster would have passed through the collision just like the galaxies, unaffected by the gas cloud's cosmic traffic jam. For MOND, however, this was a serious problem. Modified gravity ties the gravitational field directly to the distribution of visible matter. If the gravity is somewhere else, the visible matter should be there too. The Bullet Cluster presented a clear case where the map of mass and the map of light were in different places, a powerful argument for a separate, invisible substance that could become detached during cosmic collisions. An even greater test awaited in the faint, ancient glow of the cosmic microwave background. This is the afterglow of the Big Bang, a snapshot of the universe when it was only 380,000 years old, a fossilized imprint of its infancy. The precise patterns of hot and cold spots in this radiation are a treasure trove of information, encoding the exact composition, geometry, and history of the cosmos. To match these exquisitely detailed measurements, a theory needs the right ingredients in the right proportions. Dark matter, as the early structure builder, plays a starring role in this story. Its presence before the first stars formed is essential to explain the specific sizes and amplitudes of the temperature fluctuations we observe. When cosmologists run the equations of the Standard Model with dark matter included, the predicted pattern matches the observed cosmic microwave background with astonishing precision. It is a unified framework that links the universe's birth to its present structure. MOND, designed to explain galaxy rotation, struggles to replicate this success on a universal scale without significant additions. To account for the cosmic microwave background data, most MOND-like theories ultimately have to invoke some form of unseen, massive particles, essentially reintroducing a dark matter component under a different name. This suggests that while our law of gravity might need refinement in some regimes, the evidence for a vast, non-luminous component shaping the cosmos from its very first moments is overwhelming. So we are left with a stark contrast. One idea, MOND, offers an elegant solution to a specific problem, but falters when asked to explain the full breadth of cosmic evidence. The other, dark matter, provides a single, coherent actor that can explain galaxy rotation, hold clusters together, create gravitational lenses, seed the cosmic web, and imprint its signature on the first light of the universe. It is this unifying power that has made dark matter the leading paradigm in modern cosmology. Yet its very nature remains the greatest unsolved mystery in physics, a ghost we have mapped in exquisite detail but have never touched. Just as the dark matter problem was reaching a consensus, the cosmos delivered a second, even more bewildering shock. Throughout the 20th century, one of the biggest questions in cosmology was simple: what is the ultimate fate of the universe? Given the relentless pull of gravity between all galaxies, everyone expected the expansion that began with the Big Bang to be slowing down. The only debate was by how much. Would the slowdown be gradual, leading to a forever expanding but coasting cosmos? Or would it be strong enough to eventually halt the expansion and pull everything back together in a fiery big crunch? To find the answer, two independent teams of astronomers in the late 1990s turned to the universe's most reliable mile markers, a specific kind of stellar explosion called a Type Ia supernova. These are not just any exploding stars, they are cosmic standard candles. Each one occurs in a binary star system where a dense white dwarf siphons material from a companion until it reaches a very precise critical mass. At that exact threshold, it detonates in a thermonuclear blast of such consistent, predictable brightness that astronomers can calculate its intrinsic luminosity. By comparing how bright it should be to how dim it appears from Earth, they can measure its distance with extraordinary accuracy. Furthermore, by analyzing the light's redshift, how much its wavelengths have been stretched by the expansion of space, they can determine how fast the universe was expanding when the star blew up billions of years ago. It is like finding a series of identical light bulbs scattered across a vast dark plane. By seeing how faint each one looks, you know how far away it is. And by checking the color of its light, you know how much the space between you and it has stretched since the light began its journey. The two teams, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, embarked on a painstaking survey, hunting for these supernovae in galaxies billions of light years away. They were measuring the universe's expansion history, looking for the telltale deceleration. What they found, after years of meticulous observation and data analysis, was not a slowdown. It was the opposite. The most distant supernova, those whose light had been traveling for over half the age of the universe, were significantly fainter than they should have been if cosmic expansion had been slowing down or even holding steady. The only possible explanation was staggering. The expansion of the universe is not slowing down at all. It is speeding up. Some mysterious, repulsive force is pushing galaxies apart from one another at an ever-increasing rate. This was a discovery so counterintuitive, so fundamentally unexpected, that both teams spent months checking and rechecking their data for errors, convinced they must have made a mistake. But the evidence was ironclad. The universe, it seemed, contained not just an invisible mass shaping its structure, but an invisible energy stretching its very fabric. The crisis of the missing 95% had just deepened from a question of mass into a profound mystery of energy. This discovery was so revolutionary, it earned the leaders of the two teams the Nobel Prize in Physics. The mysterious force causing this runaway expansion needed a name, and scientists called it dark energy. Unlike dark matter, which pulls things together through gravity, dark energy appears to do the opposite. It acts as a kind of cosmic repulsion, a pressure inherent to the fabric of empty space itself. The most straightforward interpretation of dark energy comes straight from Einstein's own equations. Decades earlier, he had introduced a fudge factor he called the Cosmological Constant, a uniform energy density woven into the vacuum of space to keep the universe static. a notion he later called his greatest blunder. Now it seemed Einstein's blunder might be his greatest accidental prediction. A cosmological constant, a fixed property of empty space, would exert a constant, gentle pressure that, over cosmic distances, could overpower gravity and drive an accelerating expansion. It is a strange but powerful idea that the nothingness between galaxies is not truly empty, but possesses a latent energy that pushes the universe apart. The numbers involved are almost incomprehensible. When cosmologists finally tallied the complete cosmic budget, the results were staggering. Dark energy, this mysterious repulsive force, accounts for roughly 68% of the total mass energy content of the universe. Dark matter makes up about 27%, and all the ordinary matter that makes up stars, planets, and us, everything we have ever known or touched, constitutes a mere 5%. Think of the universe as a vast, dark ocean. The islands of light we call galaxies are not just floating on that ocean, they are being pushed apart by the ocean itself. The water, representing dark energy, is the dominant substance. The unseen currents beneath the surface, the dark matter, guide the island's formation. And the sparkling landmasses we can see are just a thin, glittering froth on top, a beautiful but tiny fraction of the whole. This is our new reality. The force that will ultimately dictate the fate of everything is not the familiar pull of gravity from the matter we see, but the silent, relentless push of an energy we do not understand, embedded in the emptiness between the stars. So we are left with a universe governed by two profound mysteries, one that pulls and one that pushes. To make sense of this strange new reality, scientists needed a single, coherent framework, a set of instructions that could explain everything from the faint whisper of the first light to the grand architecture of galaxy clusters today. That framework is known as the Lambda Cold Dark Matter Model, and its name tells you its entire story. Lambda, the Greek letter lambda, represents the cosmological constant, our best mathematical description for dark energy. It is that constant, gentle pressure of empty space driving the acceleration. Cold dark matter, often shortened to CDM, describes the other invisible giant. The cold means these hypothetical particles were moving slowly in the early universe, which was essential for them to clump together and form the gravitational seeds for galaxies. This simple six-letter acronym, Lambda CDM, has become the standard model of cosmology, the instruction manual for our universe, and its success is nothing short of breathtaking. This single model, with just a handful of key numbers describing the amounts of dark energy, dark matter, and ordinary matter, can accurately predict a staggering range of cosmic phenomena. It reproduces the exact pattern of hot and cold spots in the cosmic microwave background, that fossilized light from the infant cosmos. It explains the intricate cosmic web of galaxies and voids we see mapped across the sky. It accounts for the observed abundances of the lightest elements forged in the Big Bang. It even predicts how the clustering of galaxies changes over billions of years. Think of Lambda CDM as a master key. For decades, cosmologists were trying to open different cosmic doors with separate, specialized keys. One for the early universe, one for galaxy rotation, one for cluster collisions. The Lambda Cold Dark Matter Model is the single key that fits every lock, turning them all with a satisfying, unified click. It is a triumph of data-driven science, a framework so successful and so precise that it has earned the title of the standard model of cosmology. Yet for all its predictive power, this model presents us with a humbling and extraordinary truth. We have mapped the behavior of the cosmos with incredible accuracy, but we have done so using placeholders for 95% of its contents. We have built a flawless description of a reality we cannot directly perceive. But how can we possibly know the exact recipe of a universe we cannot see? The answer lies in the oldest light there is, a cosmic whisper that has been traveling for over 13 billion years. This is the cosmic microwave background radiation, and it is the single most important piece of evidence in all of cosmology. Think of it as the universe's baby picture, taken when it was a mere 380,000 years old. Before that moment, the cosmos was a searing, opaque fog of plasma, where light particles, photons, were constantly bouncing off free electrons, unable to travel in a straight line. As the universe expanded and cooled, protons and electrons finally combined to form neutral hydrogen atoms. In that instant, the fog lifted. The photons, suddenly freed, began streaming across the universe in every direction. That first flash of liberation is what we detect today as the cosmic microwave background, a faint, cold glow that uniformly bathes the entire sky. It is the afterglow of creation itself, cooled by eons of expansion to a mere 2.7 degrees above absolute zero. For decades after its accidental discovery in the 1960s, it appeared as a nearly perfect, uniform blanket of microwaves, but perfection in this case was a problem. A perfectly smooth early universe offered no clues as to how the magnificent structure we see today could have ever formed. There were no seeds, no variations, no blueprint. The breakthrough came when we learned to listen more carefully. In the early 1990s, NASA Cosmic Background Explorer satellite COBE made a historic measurement. It found that the cosmic microwave background was not perfectly uniform after all. Imprinted across the entire sky were tiny, minuscule variations in temperature, fluctuations of only about 1 part in 100,000. These were not random noise. They were the fossilized imprints of the quantum ripples from the Big Bang, the primordial seeds from which everything would grow. This discovery was a revelation, but it was only the beginning. To truly decode the message in this ancient light, we needed a map of exquisite precision. That task fell to 2 landmark space missions, the Wilkinson Microwave Anisotropy Probe, WMAP, and later, the European Space Agency's Planck satellite. These were not ordinary telescopes. They were time machines equipped with the most sensitive microwave detectors ever built, designed to scan the entire sky with incredible detail, separating the pristine cosmic signal from the foreground clutter of our own galaxy. What they produced were the most detailed baby pictures of the universe ever taken. The maps from WMAP and later, the even sharper images from Planck revealed the cosmic microwave background in stunning high definition. The subtle patterns of slightly warmer and slightly cooler spots formed a specific, intricate fingerprint across the sky. And like any fingerprint, this one contained a wealth of identifying information. Cosmologists realized these temperature fluctuations were not just a random splatter. They were a precise record of sound waves trapped in the early universe. In that hot, dense plasma, regions of slightly higher density, pulled by gravity and pushed back by radiation pressure, created standing waves of compression and rarefaction, like the ringing of a cosmic bell. The size of the spots in the cosmic microwave background map corresponds directly to the scale of these primordial sound waves at the moment the universe became transparent. By meticulously measuring the statistical properties of these spots, their sizes, their distribution, and their correlations, scientists could extract the fundamental parameters of the cosmos with astonishing accuracy. It was as if the universe had left us a detailed instruction manual written in the language of temperature. This cosmic Rosetta Stone allowed us to read off the exact composition of the universe at that early epoch. The relative heights of the peaks in the data revealed the density of ordinary matter, the baryons. The overall shape and spacing of the peaks were exquisitely sensitive to the total density of matter, both ordinary and dark. And the largest scale patterns in the map provided a measure of the universe's overall geometry, which in turn pointed directly to the influence of dark energy. The numbers that emerged were precise and definitive, ordinary matter, the stuff of stars and planets, makes up only about 4.9% of the universe's total content. Dark matter constitutes roughly 26.8%, and dark energy, the mysterious driving force of acceleration, fills the remaining 68.3%. These are not rough estimates. They are the result of fitting the Lambda cold dark matter model to the exquisitely detailed cosmic microwave background data, and the fit is spectacularly good. The pattern predicted by the model and the pattern observed in the sky align with breathtaking precision. This agreement is what elevates Lambda cold dark matter from a compelling idea to the established standard model of cosmology. We have, in a very real sense, read the recipe of the universe from its oldest light. We know the ingredients and their exact proportions with a certainty that would have been unimaginable just a few decades ago. Yet this profound knowledge comes with a profound irony. We have decoded the message, but we still do not know the true nature of the messengers, the dark matter and dark energy that dominate the cosmic ledger. Our cosmic recipe is precise, but it may not be the final word. For all its spectacular success, the Lambda cold dark matter model is now facing a subtle but growing challenge, a discrepancy that hints we might still be missing a piece of the puzzle. This new chapter in the invisible universe problem is known as the Hubble Tension, and it centers on a single, fundamental number: how fast the cosmos is expanding right now. This rate, called the Hubble constant, is the master dial for the size and age of the universe. For decades, cosmology operated under a beautiful assumption that this expansion rate should be consistent no matter how you measure it. You could look back to the infant universe, to the cosmic microwave background, and calculate what the expansion rate should have evolved into today. Or you could look at nearby stars and galaxies, measuring their distances and speeds directly to get the rate right now. In a perfectly understood cosmos, these two methods should converge on the exact same number. They do not. The tension arises from two different cosmic clocks. The first clock is set by the ancient light of the cosmic microwave background. Using the detailed Planck satellite data, scientists can run the Lambda cold dark matter model backward like a precise film reel. They take the conditions of the early universe, factor in all the known ingredients, dark energy, dark matter, ordinary matter, and let the model predict what the expansion rate should be today. This method gives a very specific answer, approximately 67 kilometers per second per megaparsec. In simpler terms, for every 3.26 million light-years you look out into space, galaxies appear to be moving away from us 67 kilometers per second faster. The second clock is built from observations in our own cosmic neighborhood. Teams use the cosmic distance ladder, a step-by-step method that starts with precise measurements of nearby stars, builds up to calibrate those type Ia supernova, and even uses subtle flickers in certain stars to gauge distances to nearby galaxies. This local measurement, championed by teams using the Hubble Space Telescope and other observatories, yields a consistently higher value, around 73 kilometers per second per megaparsec. The difference seems small, only about a 9% gap, but in the realm of cosmology, where measurements are exquisitely precise, it is a glaring and persistent discrepancy. It has withstood over a decade of scrutiny, with each team refining their methods and double-checking their data, only to find the gap remains. This is not an error bar overlap. It is a clear tension between two of the most trusted pillars of modern cosmology. One tells the story from the universe's first breath, the other from its present moment, and they disagree on how quickly it has grown up. So what could this mean? If the measurements are both correct, then the Lambda cold dark matter model, as it stands, might be incomplete. Perhaps dark energy is not a constant after all, but something that changes over time, evolving in a way we have not accounted for. Maybe dark matter has properties more complex than simple coldness, interacting with itself, or with radiation in subtle ways that tweak the expansion history. Or there could be an entirely new ingredient in the cosmic soup, a relic particle from the early universe or a modification to gravity that only manifests across vast ages. The Hubble tension is a quiet but insistent alarm bell. It reminds us that mapping the universe's behavior is one thing, but fully understanding the actors behind the curtain is another. We have identified the dominant players, dark matter and dark energy, but we may not yet know all their lines in the cosmic script. This tension is not a failure of science. It is the process of science at its most vital, a clue that the next great discovery in cosmology is waiting just beyond the edge of our current model. The silence from those deep underground laboratories is growing louder with each passing year. After decades of operation, with detectors of breathtaking sensitivity listening for the faintest nuclear whisper, the expected signal from weakly interacting massive particles has simply not arrived. This profound non-detection is forcing a pivotal moment in the hunt. It suggests one of two equally revolutionary possibilities. Either dark matter is even more elusive than our most conservative WIMP models predicted, a ghost that interacts so weakly it borders on the undetectable, or our entire conceptual framework for what it could be needs a fundamental rethink. The WIMP, for so long the favored candidate, is now under immense pressure. Scientists are beginning to explore the darker, more exotic corners of theoretical physics. Could dark matter be composed of ultra-light particles like axions, with trillions streaming through your hand every second, but each with so little mass that detecting one is like trying to feel the impact of a single raindrop? Or perhaps it is made of primordial black holes, remnants of the universe's violent first moments, lurking unseen in the darkness. There is even the speculative idea of a whole dark sector, a hidden universe of particles and forces parallel to our own, interacting with us only through gravity. This shift in thinking is sparking a new wave of experimental creativity. If dark matter is not a WIMP, we need entirely new kinds of traps. Some researchers are designing experiments to look for the minuscule electric fields that an ultra-light action might generate. Others are repurposing vast networks of precision sensors, like global positioning system satellites or sensitive atomic clocks, to look for subtle distortions that might reveal a passing dark matter clump. The hunt is not ending, it is evolving. It is moving from a targeted search for a specific kind of ghost to a broader exploration of the shadows, testing the limits of our ingenuity as we try to build a net fine enough to catch something we can barely describe. The longer the silence persists, the more we are forced to confront a humbling truth. The hidden universe may be stranger and more cleverly hidden than we ever dared to imagine. While the underground labs listen in silence, the cosmos itself continues to conduct its own experiments on a grand scale. Astronomers have become cosmic detectives, using the universe as their laboratory to probe the very nature of the invisible stuff. Their tools are not vats of xenon, but the faintest, most pristine galaxies and the delicate traceries of ancient star streams. These astrophysical probes are testing the core assumptions of the cold dark matter model, asking if the ghost is truly as simple and aloof as we think. The first and perhaps most powerful laboratories are the dwarf spheroidal galaxies that orbit our Milky Way. These are not majestic spirals, but faint, wispy collections of a few million ancient stars. Their significance is profound. They are believed to be over 99% dark matter by mass. With so few stars to create complex astrophysical noise, they are nearly pure reservoirs of the hidden substance. By measuring the motions of their stars, astronomers can map the distribution of dark matter within them with incredible precision. The results place tight constraints on what dark matter can be. If the particles were warm, meaning they moved at significant speeds in the early universe, they would have smoothed out these small clumps, preventing tiny dwarf galaxies from forming at all. The very existence of these numerous faint satellites strongly supports the cold hypothesis that dark matter was slow-moving and readily clumped. But within these dark matter dominions, other questions arise. The Standard Model predicts that dark matter is not only cold but collisionless, meaning the particles pass right through each other like ghosts in the night. This should cause dark matter to pile up in the centers of galaxies, creating steep density peaks or cusps. Yet, observations of some dwarf galaxy cores suggest a smoother, flatter distribution, more like a gentle hill than a sharp peak. This subtle discrepancy is a tantalizing clue. Could it be that dark matter particles do interact with each other just a tiny bit through some unknown force? Even a faint self-interaction could scatter particles and smooth out those central cusps. It is a delicate measurement, like trying to discern the shape of a shadow by watching how moths flutter around its edges, but it is one of the few ways we have to test the collisionless assumption itself. Another exquisite probe comes from within our own galactic halo. The Milky Way is not just surrounded by a smooth cloud of dark matter. The theory predicts it should be teeming with thousands of invisible subhalos, clumps of dark matter that never collected enough gas to form stars. We cannot see these dark clumps directly, but we can see their gravitational effects on the things we can see. Throughout the halo, there are long, beautiful ribbons of stars known as stellar streams. These are the remnants of small globular clusters or dwarf galaxies that were torn apart by the Milky Way's gravity, their stars strung out along their orbital path like pearls on a cosmic necklace. In a perfectly smooth dark matter halo, these streams would be pristine and linear. But if an invisible dark matter subhalo plows through one of these streams, its gravity will tug on the stars, creating a visible kink, gap, or fanning effect in the ribbon of light. Astronomers are now scanning the sky, hunting for these subtle disturbances. Finding them is like seeing the wake of an invisible ship passing through a sea of stars. Each detected disturbance maps the location and mass of a dark matter subhalo, providing a census of the invisible population predicted by the theory. So far, a handful of promising candidates have been found, their ghostly passages etched into the stellar currents. This is not just mapping the dark matter, it is taking its fingerprint, learning about the size and distribution of its smallest structures. Every faint dwarf galaxy, every disturbed stellar stream adds another data point. Together, they are building a profile of our hidden cosmic neighbor, not by catching it, but by meticulously recording the subtle ways it bends the visible world to its unseen will. Yet for all its mathematical elegance, the cosmological constant is a confession of ignorance. It is a placeholder, a label we give to a force we do not understand, a simple number plugged into equations to make them match the accelerating reality we observe. While both dark matter and dark energy share the word dark, meaning unseen, they could not be more different in nature. Dark matter is clumpy. It gathers under gravity, forming the hidden scaffolding of galaxies and clusters. You can think of it as a vast, invisible mountain range shaping the cosmic landscape. Dark energy, by stark contrast, appears to be perfectly smooth and uniform. It is not concentrated in galaxies or voids. It is a property of empty space itself, a latent energy infused into the vacuum between every particle, every star, every galaxy. Its effect is not to pull things together, but to push them apart, acting as a form of repulsive gravity on the largest scales. This is why its discovery was so shocking. It revealed that the dominant force in the cosmos, making up over 2/3 of everything, is a kind of anti-gravity, steadily stretching the fabric of the universe. The cosmological constant is the simplest explanation, but it raises profound, almost philosophical questions. Why does empty space have this energy? And why is its value so incredibly precisely tuned? If it were just slightly stronger, the universe would have blown itself apart before any stars could form. If it were slightly weaker, gravity would have recollapsed everything long ago. This fine-tuning seems like a cosmic coincidence of staggering proportions, leading many scientists to wonder if the constant is truly constant at all. This question has given rise to a compelling alternative theory known as quintessence. Imagine if dark energy is not a fixed feature of space, but a dynamic energy field that permeates the cosmos, a kind of fifth fundamental force that can change in strength over time. The name quintessence comes from the ancient idea of a fifth element beyond Earth, air, fire, and water, a celestial substance. In this modern theory, the repulsive force driving cosmic acceleration could have been different in the past and may evolve in the future. It could weaken, allowing gravity to reassert itself, or it could grow stronger, leading to a far more dramatic and violent end for the cosmos. Quintessence offers a way to potentially explain the fine-tuning, as the field could have naturally evolved to its current state. It also provides a possible, though highly speculative, link to resolve the Hubble tension, that nagging discrepancy in the expansion rate. If dark energy's strength has changed slightly over cosmic history, it could tweak the expansion just enough to make the early universe and the modern universe measurements align. The challenge, of course, is that both the cosmological constant and quintessence fit the existing data almost equally well. Distinguishing between a static vacuum energy and a dynamic field is one of the paramount goals of next-generation observatories. They will peer deeper into the past, measuring the expansion history with even more precision, searching for any subtle sign that the push of dark energy has ever wavered. So we are left with a staggering reality. The fate of everything from the largest galaxy cluster to the smallest atom appears to be held in the balance by an energy we cannot see, barely understand, and cannot yet fully describe. Is it a fixed feature of the void or a shifting field with a mind of its own? The answer will determine not just the history of our universe, but its ultimate destiny. The search for the hidden universe is about to leap forward with a new generation of cosmic observatories. These are not just upgrades, they are revolutionary instruments designed to map the invisible with a precision we have never before achieved. Their goal is to move from knowing the dark universe is there to understanding exactly how it behaves particle by particle, force by force. Leading this charge from the ground is the Vera Rubin Observatory in Chile. Its centerpiece is the Legacy Survey of Space and Time, a 10-year mission that will utterly transform our view of the sky. Using the largest digital camera ever built, it will scan the entire southern sky every few nights, creating an unprecedented motion picture of the cosmos. It will catalog billions of galaxies, trace the cosmic web in exquisite detail, and discover millions of supernova. For dark matter, its power lies in weak gravitational lensing on a colossal scale. By measuring how the images of countless distant galaxies are subtly distorted by the dark matter halos of foreground structures, Rubin will create the most detailed mass map of the universe ever made. It will see the invisible scaffolding in high definition, testing whether dark matter truly behaves in a simple, cold, and collisionless way, or if its distribution reveals hints of unexpected interactions. For dark energy, the survey's sheer volume of supernova and its ability to measure how galaxy clustering changes over cosmic time will provide the most stringent test yet of whether the acceleration is driven by a simple cosmological constant or a dynamic force like quintessence. It will measure the expansion history of the universe with a finer comb, directly addressing the Hubble tension. In space, two pioneering missions will take complementary approaches. The European Space Agency's Euclid telescope, already launched, is a specialist in cosmic cartography. It is meticulously measuring the shapes and redshifts of over 1 billion galaxies to construct a three-dimensional map of the universe spanning 10 billion light-years. Its primary tool is again weak lensing, but with the crystal-clear vision only space can provide, free from the blurring effects of Earth's atmosphere. Euclid will trace the growth of cosmic structure across time, watching how dark matter's gravitational wells deepen and how dark energy's repulsive push fights against that growth. Following later this decade, NASA's Nancy Grace Roman Space Telescope will be a wide-field infrared powerhouse. It will perform its own enormous galaxy survey and supernova hunt, but with a unique capacity to peer through dusty regions of space and see the universe in infrared light. Roman will study the most distant supernova to pin down the expansion history, and it has a special talent for a phenomenon called microlensing. By monitoring hundreds of millions of stars for the brief brightening caused by intervening dark objects, Roman could finally solve the mystery of whether some dark matter is in the form of primordial black holes or rule them out entirely. And looking back to the very beginning, next-generation experiments are focusing on the cosmic microwave background with microscopic precision. Projects like the Simons Observatory in Chile and the planned CMB Stage 4 experiment will deploy arrays of hundreds of thousands of superconducting detectors to map the CMB's polarization, the directional imprint of those primordial sound waves with breathtaking sensitivity. These subtle polarization patterns hold clues to the mass of neutrinos, the potential presence of primordial gravitational waves, and any faint signatures of dark matter interacting with radiation in the universe's first moments. Together, this suite of instruments represents a coordinated assault on the dark universe. They will measure the push of dark energy and the pull of dark matter not as single numbers, but as evolving stories written across the sky. They will cross-check each other's findings using different techniques to corner the same truth. We are building eyes that can see the shape of emptiness and trace the history of shadows, hoping that in the flood of new data, the ghosts will finally have to show their hands. But where do you go when experiments see nothing and the universe's own clues point toward something stranger? You venture into the realm of pure theory, where the map of reality is redrawn with equations. The profound mystery of the dark universe is not just a problem for astronomers. It is a siren call for theoretical physicists, pulling them toward ideas that sound like science fiction, but could be the next chapter in our understanding of everything. These are not just new particles, but new principles. One of the most ambitious frameworks is string theory. At its heart, it proposes that the fundamental ingredients of the universe are not point-like particles, but unimaginably tiny, vibrating loops of energy. The different vibrations of these strings would correspond to all the particles and forces we know, from electrons to photons. But for this elegant mathematics to work, string theory requires more dimensions than the 3 of space and 1 of time we experience. It suggests there could be 6 or 7 extra spatial dimensions, curled up and hidden at scales far smaller than an atom. This is where a speculative connection to dark matter and dark energy emerges. What if the particles we call dark matter are actually vibrations confined to these hidden dimensions, only able to interact with our world through the universal glue of gravity? Or perhaps dark energy is a manifestation of the energy contained in the shape and stability of these extra dimensions themselves. While these ideas are far from proven, they illustrate how the dark universe problem forces us to contemplate architectures of reality that are utterly alien to our everyday experience. An even more radical idea comes from the holographic principle, born from the study of black holes. It suggests that all the information contained within a volume of space can be thought of as encoded on its 2-dimensional boundary, like a cosmic DVD where a 3-dimensional movie is stored on a flat surface. Applied to the universe, this principle hints that our 3-dimensional reality, with its dark energy and dark matter, might be a projection of information stored on a distant 2-dimensional surface. In such a view, dark energy might not be an energy in space, but a consequence of how information is processed on that fundamental surface as the universe expands. It reframes the mystery from what the dark stuff is to how the cosmic code is being rendered. Then there is the concept of emergent gravity, championed by theorists like Eric Verland. This idea turns the problem completely on its head. What if gravity itself is not a fundamental force, but an emergent phenomenon, a side effect of the way information and quantum entanglement are organized in the universe, much like temperature emerges from the collective motion of molecules? In this view, the effects we attribute to dark matter are not caused by invisible particles at all. Instead, they are what happens when our current equations for gravity, which work perfectly well in the solar system, fail to account for this deeper, information-based origin in the extremely weak gravity regimes of galaxies and clusters. The extra gravitational pull we measure would emerge naturally from the universe's quantum information structure, making dark matter an illusion, a gravitational mirage. These theoretical frontiers are not yet answers. They are pathways, thought experiments that stretch our imagination to its limits. They show that the dark universe crisis is more than a missing piece in a puzzle. It is a sign that the puzzle itself might be part of a much larger and far stranger picture we are only beginning to glimpse. This leaves us standing before a cosmic mirror, and the reflection is deeply humbling. For all our technology, our ambition, and our intricate theories, the universe presents us with a simple, staggering fact. We are made of the rarest stuff in existence, the ordinary matter that forms every mountain, every ocean, every star in the night sky, and every thought in your mind constitutes less than 5% of the cosmos. In the grand accounting of reality, we are not the main event. We are a delicate afterthought, a rare and luminous contaminant adrift in a vast, dark sea whose true nature remains utterly foreign to us. This is perhaps the most profound philosophical shift in human history. We once believed the heavens were made for us, that the stars and planets were literal guides or deities. Then we learned we were not the center of the universe. Now we have discovered we are not even made of the same material as most of the universe. Our very substance is the cosmic exception, not the rule. This transforms our place from central actors to curious observers of a play where most of the characters are invisible, and the script is written in a language we have only just begun to decipher. It raises a haunting question about the nature of knowledge itself. Is our current ignorance about dark matter and dark energy merely a temporary stage, a puzzle that sharper telescopes and more clever experiments will eventually solve? Or does it point to a more fundamental limit, a horizon beyond which human perception and cognition simply cannot reach? We are beings evolved to understand the world of medium-sized objects moving at modest speeds, a world of solid matter and clear light. Our intuition and the physics born from it is exquisitely tuned to that realm. Yet the universe, in its majority, operates on scales and under principles that have no analog in our daily experience. Can a mind shaped by a 5% reality ever fully comprehend the 95%? This is not a call for surrender, but for a new kind of humility and ambition. Every unanswered question is an invitation. The darkness is not an emptiness but a frontier. It tells us that reality is far richer, far stranger, and far more mysterious than we ever dreamed. To live in such a universe is to accept that wonder is not a temporary state of childhood, but the permanent condition of a cosmos that keeps its greatest secrets just out of sight, compelling us to look deeper, think harder, and imagine wider than we ever thought possible. So the revolution sparked by that missing mass is far from over. What began as a puzzling anomaly in galaxy clusters has transformed into the defining narrative of modern cosmology, a story of subtraction that revealed a universe utterly alien to our senses. We have journeyed from the first confusing clues in spinning galaxies to a grand, mathematically precise model, that can describe the cosmos from its first whisper to its present grandeur. The Lambda Cold Dark Matter Framework is a monumental achievement, a testament to human curiosity and ingenuity. It is the map that fits every landmark, from the cosmic microwave background to the bullet cluster, telling us with astonishing certainty that we are surrounded by a dark ocean where our islands of light are rare exceptions. Yet this very success has deepened the mystery. We have not solved the invisible mass problem, we have simply given it a name and a job description. Dark matter builds, dark energy pushes, and together they govern everything, but we have no idea what they truly are. The revolution has evolved from a search for missing mass into a far more profound quest to understand the fundamental constituents of reality itself. The Hubble tension, that stubborn discrepancy in the expansion rate, is a quiet but insistent reminder that our map, for all its beauty, may still be missing a contour line or two. It tells us the story is still being written. This ongoing transformation, this drive to explain the dark majority, is what keeps cosmology vibrantly alive. Every silent underground detector, every new sky survey peering deeper into the past, every theoretical leap into extra dimensions or emergent gravity is a step into that darkness. We are not at the end of this journey. We are in its most exciting chapter, where each answered question reveals 3 new ones, and the universe continues to guard its deepest secrets just beyond the edge of our understanding. That pursuit of the invisible has rewritten our cosmic story. From a universe of familiar stars and gravity, we have arrived at a reality defined by its shadows, a cosmos where the known is the exception and the mysterious is the rule. This journey from confusion to the Lambda Cold Dark Matter model is one of science's greatest triumphs, a testament to our ability to map what we cannot see with breathtaking precision. Yet the map is not the territory. We have the instructions, but we still do not know the true nature of the ingredients. This is not a failure, it is the very engine of discovery. The Standard Model is a powerful, living framework, precise enough to make stunning predictions yet incomplete enough to drive the next generation of telescopes, experiments, and bold ideas. It is a story still being written, with every unanswered question a new paragraph, every anomaly a potential plot twist. So the next time you look up at the night sky, remember you are not just looking at points of light. You are gazing at the luminous tip of a vast, dark iceberg. Those stars and galaxies are the visible traces of a hidden architecture, shaped by matter that does not shine and pushed apart by an energy we do not understand. That silent, dominant cosmos invites your curiosity. It asks you to wonder what lies in the darkness between the stars. To follow this grand adventure, all you need to do is stay curious and watch as humanity's greatest detective story continues to unfold.